In this video, we will solve the linear programming problem using graphical method, and we will take the case where we have the multiple solutions. Okay. So in the earlier video, we got a unique solution. So let us say we have a question that is we want to maximize our objective function, that is z is equal to 5x1 plus 10x2, and we have the constraints here, that is x1 plus 2x2 is less or equal to 120, x1 plus x2 is greater or equal to 60, x1 minus 2x2 is greater or equal to 0, and we have the non-negative restrictions, that is x1 and x2 are greater or equal to 0. So first thing is what we do, we take these constraints and draw them on the graph. Okay, so to solve them, what will we do? Simply for the first equations, we have x1 plus 2x2, we set it first equal to 0, then we solve. Okay, so here you can see for x1 and x2 what will we get the values when x1 is equal to, so here we have rather 120, sorry, so we remove the inequality to find out the coordinates on the graph. Okay, so when x1 is equal to 0, that means 2x2 is equal to 120, which means x2 is equal to 60. Okay, so when x1 is equal to 0, x2 is equal to 60. Similarly, when x2 is equal to 0, so this term is equal to 0, that means x1 will be equal to 120. So when x2 is equal to 0, here we will get 120 for the first constraint. Okay, so we have x1 is 120. So let me show it here. Let us say this point denotes 120, and our x1, here you can see, rather our x1 is 120 and x2 is 60. Let us say this point is 60. We draw these 2 pointers, rather we join these 2 pointers, we get the graph for x1 plus 2x2 is equal to 120. Next thing is we take the second constraint and set it equal to 0, that is x1 plus x2 is equal to 60, and we draw the pointers, that is we have x1, x2. So when x1 is equal to 0, in this equation x2 will be equal to 60, and when x2 is equal to 0, x1 will be 60. Okay, so we have 60 on x1, so let us say this point is 60, and x2 which is also 60 here again, then we join these two like this, we get the graph for this very equation. Next we have x1 minus 2x2. So we have x1 minus, rather let me use another color, x1 minus 2x2 is equal to 0, which means x1 is equal to 2x2. Okay, so what are the pointers here for x1 and x2? Let us see. So let us take x1 and x2. So when x1 is equal to 0, x2 will be equal to 0. Similarly, let us take some pointers here. Let us say when x2 is equal to 5, if x2 is equal to 5, that means x1 will be equal to 5 into 2, which is equal to 10. Similarly, when x2 is equal to 10, x1 will be twice, rather when x2 is equal to 10, x1 will be 2 into 10, which is 20. Okay, so we will get multiple, we will get this kind of line, and let me try to draw it like this. Okay, now we need to find out the feasible region, the common what is feasible region? The area what we call the feasible region, the area that satisfies all the constraints of the problem. That is our objective function. We call that very area as feasible area, okay, or feasible region. Simply the area that satisfies all the constraints of the objective function, we call that very area is the feasible area. Now in the first case we have x1 plus 2x2. Since we have this inequality sign, okay, we have less or equal to 0, less or, so let me put it simple thing. When we have this less or equal to sign, this sign, and we have, let us say, this very line, now it is shaded part, we shade the area below, okay, so in this direction we shade the area. If we have again, if we have another line, let us say again this line, and in this case if we have greater or equal to sign, our shaded area will be this very area, okay, we shade the upper region. Now let us see what happened here. So x1 plus 2x2 is less or equal to this very thing. So this is our equation. So we shade the below area, this area. In the second we have x1 plus x2 greater than 0. So x1 plus x2 rather greater or equal to 60. So we have to shade the above area, that means this area. In the third one, let us see. So can we write x1 is greater or equal to 2x2. So in this case, if this is the case, then the shaded area will be this area. Now we need to find out the common area. Okay, the feasible region is the area that satisfies all the constraints. Here you can see, so common area will be this very quadrilateral. Okay, so this will be our feasible region. Here you can see all the constraints are satisfied, because for the red line we share this portion, for the black line this region, and for the green line this region. So this will be our feasible region. Okay, this is our feasible region. Now we need to find out the coordinates, and let us write the coordinates. What were the coordinates here? So let us say this is point, let us say this is our point. So for this it was here 60. So let us say we have this is point A, this is point B, this is point C, and this is point D. For A we have the coordinate says 60, 0. For B we have 120, 0. So our optimal solution will lie, rather our optimal solution will be either at this point, this point, this point, or this, because this is the shaded region. So the line is joining the shaded region denote the set of pointers that are the feasible solutions here. Okay, so and we need to find out which of these is actually the feasible solution. So we have the coordinates of A, B, but we need to find out the coordinates of C. To find out the coordinates of C, what will we do? Since x1 is equal to 2x2, we plug the value of this in this equation to find. So we have this line, this line corresponds to x1 plus 2x2 is equal to 120. So we take this equation rather, and this equation. So these two intersect at this point. We solve these two, that is x1 plus 2x2 is equal to 120 and x1 is equal to 2x2 to find out the coordinates of point C. So x1 is equal to 2x2, plug it in this equation, so we get 2x2 plus 2x2 is equal to 120, or 4x2 is equal to 120, dividing both sides by 4, x2 will be equal to 30. That means x1 will be equal to 60. So the coordinates of point C are 60 and 30. What about the coordinates of point D? So we have the red line. Red line corresponds to x1 plus x2 is equal to 60, and we have this green line, it corresponds to x1 is equal to 2x2. Solving this, plug the value of x is equal to 2x2 in this equation, so we get 2x2 plus x2 is equal to 60, or 3x2 is equal to 60, or x2 will be equal to 60 upon 3, which is 20. That means x1 will be equal to 2 into 20 is 40. So the coordinates are 40, 20. So here we have the coordinates is for 40, 20. This point does not correspond. This point doesn't represent our feasible point because it is outside the feasible region. Okay, so we have these 4 points which are our feasible points here. Okay, now let me rub this out. Now we need to find out the optimal solution if it exists in this equation. Okay, so for we have the maximization problem. Z is equal to 5x1 plus 10x2. We evaluate the objective function at each of these points to see whether we have one unique solution or multiple solutions. So let us take point A. At A we have the coordinates is 60 for x1, 0 for x2. That means Z will be equal to 5 times 60 plus 10 times x2 is 0. So this gives us 5 6 are 30, so we get 300 here. Now let us take point B. At point B we have the coordinates is 120 comma 0, so Z will be equal to 5 into 120 plus 10 into 0. So this is here 5 zeros are 0, 5 2s are 10, 5 1s are 5, which is equal to 600. So Z is equal to 600 at this point. Now let us take the point C. At C we have 60, 30. So Z will be equal to 5 into 60 plus 10 into 30. So here we get 5 6 is 30. So 300 plus 10 into 30 is 300. So Z again comes out to be 600. So at this point Z is equal to 600, rather no, at this point Z is equal to 600, and at this point also Z came out to be 600. And let us evaluate it at point D. So at point D, so the coordinates of D are 40 comma 20. So let us see, Z will be equal to 5 into 40 plus 10 into 20. So we will get here 5 into 40, 5 4 are, which is 200 plus 200, we will get 400. So at this point Z is equal to 400. Obviously you can see at point C and at point B we get Z is equal to 600 and 600. So we got two optimal solutions, or we got the optimal solutions. In this case we did not got a unique solution, only one solution. Here we got two solutions. So that is when x1 is equal to 120, x2 is equal to 0. This was one solution, and another solution was when x1 is equal to 60, x2 is equal to 30, because at these points we get the same maximum value. Now why does this happen? So how do we recognize whether the given linear programming problem has multiple solutions? Simple thing, multiple solutions occur when the slope of, or let me write it like this, let me put it like this, when the objective function is parallel to one of the binding constraints, then we will have the multiple solutions. Or in other words, when the slope of the objective function is parallel to one of the binding constraints, in that case also we get multiple solutions. So what is the slope of objective function? You can find out. So z is equal to 5x1 plus 10x2. okay, so x2 is this, x1 is this, so slope will be x2 upon x1, so we get 10 upon 2 is the slope, which is equal to 5 of the objective function, and here we will 10 upon 2 is 5. Rather we have 10 upon 5, sorry for this mistake. The slope of this line will be equal to, that is x2 upon x1, which is equal to 10 upon 5, which is equal to 2. And here you can see this constraint, that is x1 plus 2x2 is equal to 120. It has also a slope of, because x2 is 2, x1 is 1, so we have x2 upon x1 is equal to 2 upon 1, which is equal to 2. Since the slope of the objective function and one of the binding constraint are equal, in this case we can get the multiple solutions. In fact, the point connecting C and B, any point on this region, will give us the same maximum value of 600. okay, I cannot show it here because I don't have what I can say, the numbering or the perfect numbering given. So any combination of x2 and x1, any point here will give us the value of z is equal to 600. okay, so simple thing. To see whether a graphic or a linear programming problem has multiple solution, just check the slope of the objective function and the slope of the binding constraints. If they are equal, then we will have multiple solutions. I hope I make myself clear in this video. Thank you.